two-dimensional gel electrophoresis. Two-dimensional gel electrophoresis has been instrumental in the birth and developments of proteomics, although it is no longer the exclusive separation tool used in the field of proteomics. One of the first reports of successful two-dimensional electrophoresis coupling IEF, that is isoelectric focusing, to SDS page sodium dodecyl sulfate polyacrylamide gel electrophoresis was published 1974, but unnoticed because of two features. The first one was the inclusion of the sample within the IEF tube gel, which is a quite efficient but slightly cumbersome process. The second was the detection method, that is the classical coercive blue staining in alcohol acid mixtures. However, a report by O'Farrell 1975 using a cathodic sample application and showing hundreds of distinct spots through the use of autoradiography of 35S labeled proteins was accepted. The resolution was much greater than with other two-dimensional techniques. Example, those using native IEF or those using another type of zone electrophoresis as the first dimension. However, two core features of these early days had very strong consequences. The first one is the rather poor reproducibility of IEF with carrier ampholytes, which is prone to several problems such as cathodic drift. The second one was the absence of technique enabling to identify a specific protein spot on a 2D gel. These two major pitfalls were the subject of intense research that succeeded at the ends of 80s, on the one hand with the introduction of immobilized pH gradients and on the other hand with protein identification with advanced sequencing. With protein sequencing, it became possible to identify spots on 2D gels almost at will, although it was much more labor intensive and less sensitive with advanced sequencing that it is now with mass spectrometry, which also achieved a quantum leap in speed, sensitivity and depth of protein characterization after 2D electrophoresis. Basic concept. The basic concept of 2D electrophoresis is shown in figure 1. 2D electrophoresis suggests that it is two-step process. It is indeed a 5-step process. First, sample preparation prior to the first separation. Second, first separation. Third, interfacing with the second separation. Fourth, second separation, and fifth, protein detection. Generally, the order of separations is first IEF and second SDS electrophoresis. Both are very sensitive to the presence of ampholytes and of non-ionic detergents, two types of chemicals that are almost indispensable in denaturing isoelectric focusing, but are limited to the buffer front when the classical order of separations is used. Sample preparation. As the first separation is always almost isoelectric focusing, it brings two types of constraints. First of all, the charge of the proteins must not be altered in any way. A combination of shower drops and detergents is almost always used for this. Shower drops are excellent protein denaturing and solubilizing agents and neutral shower drops such as urea. However, shower drops alone are not sufficient as they do not dissolve cellular lipids efficiently and are not able to keep proteins soluble enough under the conditions prevailing in IEF. To achieve both purposes, electrically neutral detergents are always added during sample preparation. Any type of detergent completely neutral over the whole pH range of IEF and compatible with the shower drops can be used. Example, CHAPS 3,3-cholamidopropyl dimethylammonio 1-propane sulfate. The second important point that has profound consequences is that the fact that IEF operates at very high field strength due to the fact that the charge of the proteins continuously decreases. Thus, to make them travel very high electric fields, 170 volt per centimeter must be used in IEF compared to SDS electrophoresis, 15 volt per centimeter. Finally, sample preparation concerns protein modification. These can be by chemical modification. Example, carbamylation induced by the presence of urea, and this is indeed more a problem during sample preparation and storage than during 2D electrophoresis itself. Isoelectric focusing. As IEF is a steady state technique, the sample can be theoretically applied at any point of the pH gradient without altering the final result. The sample is generally applied at one of the extremities of the pH gradient or dispersed with the IEF gel. In carrier ampholytes based focusing, dispersion requires to include the sample in the gel during the polymerization of the gel itself. Voltage profile is a direct consequence of the high field strengths that must be used in IEF. Quite often, biological samples are not completely desalted and the salts present can induce a strong Joule heating if high field strength is applied at once. This is also true at a lesser extent for the ampholytes that are used as conductivity smootheners, which must reach their isoelectric point. For both salts and ampholytes, advantage is taken of their high mobility compared to proteins and moderate field strength is used for some time, typically 15 volt per centimeter for 3 hours to allow them to reach their final position. Then the high field strength is applied.